Okay, today we discuss about the topic number 2, endogeneity. So what's the meaning of the endogeneity? So endogeneity means that when externally variable in our model is correlated to the error term. Error term. So means that, let's say this is our model, and the yi equal to beta o plus beta 1 x 1i plus beta 2 x2i. Okay, let's say this is our model, and when the one or two or maybe all the exponential variable in our model is correlated to the error term, so means that there is the endogeneity problem in our model. We call this problem because one of our assumption, and when we using the OLS, we assume that there is no correlation exists between the exponential variable to the error term. Okay, if this happen, the x1 is correlated to the error term, and we still using the OLS, means that maybe the result or the coefficient estimated we get from this regression could be biased. Could be biased. So of course in this case, when one or more exponential variable is correlated to the error term, means that we cannot using the OLS. We cannot using OLS. We need to using the another method to estimate this equation or this equation. If we still use LS, of course the value of the beta 1 and beta 2 could be biased, because the correlation between exponential variable to the error term means that we avoid the assumption, one of the assumption when we doing the OLS. Okay. Okay, so so and then what's the sources of the endogeneity problem? Okay, this one you can read yourself. You can read yourself. The note I given to you. The one is measurement error, and then simultaneous duplication bias, and number 3 is omitted variable. So these three factor contribute why the exponential variable is correlated to the error term. Okay, now we want to look how we want to handle this problem. Like say this is our model, and we can see that it's clearly so that the x1 is correlated to the error term. So what we should do now? How want to overcome, or how want to handle this problem when we face something like this? Okay, so the problem for the least square arises when the x is random and is correlated to the random distribution, E, in our model. Okay, so in this case, let's say if this happen, so means that our in this case, when the s is correlated to error term, so it means that the correlation between the x1 and the error is not equal to 0. It's not equal to 0. So means that this is referred to the endogeneity problem. This is referred to the endogeneity lah. Is referred to the endogeneity in our model. Refer to the endogeneity in our model. Okay, so in this case, if this happens, so you will need to get the instrument variable. This is the strategy. This is the strategy how we want to overcome the problem of the endogeneity. Means that we need to get the another variable outside the system, or means that the variable must be outside from this equation to treat as a instrument. We treat this variable as the instrument. As instrument. So means that what's the meaning of the instrument? Instrument means that we must make sure that the correlation between x1 and the z, like say z is referred to the instrument variable, z is referred to the instrument variable which we get from outside the system, must be is in not equal to 0. So means that there is the high correlation between x and the z. We must have the z variable must be highly correlated to the x, and of course at the same time you must make sure that the correlation between the z and the error of course must be equal to 0. So means that the z is not correlated to the error. This one is not correlated to the error. So if z is correlated to the error, so means that the unity problem is still exists. The problem cannot be solved. The problem is still there. It cannot be solved. Okay, so means that the strategy is where the strategy is we need to get the instrument variable. We call it as the instrument variable IV. And then IV, let's say we denote it by the z lah, by the z to instrument for the x1. Instrument for the x1, and then of course the z must be fulfill the what you call it, the condition. The z must be the fulfill the condition. The first one is highly correlated to the x, and the second one is not correlated to the error. So if we have get the instrument variable, the z, so means that we can using what we call it as the instrument variable estimation. Instrument variable estimation. So this one this refer to the z does not have the direct on y, okay, and then the z is not correlated to the error, must be exogeneity, must be strictly exogeneity, and number 3 is of course the z must be correlated to the x. The z must be correlated to the x. If we have get something like this, means that we can doing the instrument variable estimation, but of course we need to get the variable z. We need to get the variable z, and then test variable z must be confirmed, that must make sure that is not include the original model, not include in the original model. The z must be outside from the equation, from the original equation or original model. Okay. So the variable z with this property, we call it as the instrument variable. So means that if the z is fulfill this property, correlated to the x and not correlated to the error, so the z we call it as the instrument variable. So this is terminology arise because I took z does not have the direct effect on y. Of course, there is not direct effect on y. Because why we say that does not have the direct effect? Because the z actually is not included in the original model. Look this one. The z is not directly and is not included into the original model. We are using the z as a tool, to replace the not directly replace it, indirectly replace of the x1, indirectly replace as the one. So it's as a tool or as an instrument that we are using to achieve our objective. Okay, if the such a variable z exists, then we can use it from the moment condition moment condition, something like this. The z v equal to 0, and this is the moment, and the sample moment condition is something like this, and of course the equation 2.33 is referred to the formula how we using the instrument variable estimation. This is the formula actually. This is the formula how we want to estimate the coefficient of beta O and beta 1 using the instrument variable. We can see that the value of the x now is replaced by the z as a instrument. Look this one, by the z as the instrument. Okay, and then of course this new estimator have the following properties. The first one, they are consistent if z is exogenous. If the z is not exogenous, of course the parameter estimated you get is not consistent It's not consistent. So we must make sure that the z is not correlated. The z, this one, is not correlated to the error. The z is not correlated to the error. must be equal to 0. Not correlated. Okay. And then to implement the instrument variable estimation in the multiple regress equation, we need to estimation formula that is more general than 5.3 lah. 5.3. Okay, consider the multiple regression model something like this. We have the x1, x2, and 3. So means that we have the 3 explanatory variable, and then we know that we suspect that the x1 is endogenous variable correlated with the error term. So means that x1 is endogenous. In this case, we assume that the S1 is endogenous, and then this one x1 endogenous and is correlated to the error. So the variable x2 and x3 are exogenous. Means that we assume that the x2 and x3 is not correlated to the error. So in this case, for our this model, only one variable is correlated to the error. Is referred to the S1 lah. S1. Okay. So instrument variable estimation can be carried out using the two-step process. Okay, this is the process or the two-step we must doing when we want to using the instrument variable. Okay, the first one is first stage regression. So means that, okay, let's say this is our model. This is our model. Okay, I want to show you not model actually. Okay, let's say this one. Y I beta O plus beta 1 x 1 I. Okay, this is our model, and then of course we assume that the x1 is correlated to the error. X1 is correlated to error. So in this to doing the instrument variable, like I said before, we need to the z variable, and then that z variable must be outside from the original equation. In other words, it's not included in the original model. The z must not include in the original model. It's outside from the system or outside from our equation. And then of course there's two condition must be fulfilled when we want to using the z as an instrument for the S1. The first one is the z must be highly correlated to the x. Must be highly correlated to the x. And the second one is the z is not correlated to the error. Not correlated to the error. Okay, now we want to look how we want to perform the two-stage estimation. As two-stage estimation. Okay, the first one is x1 on the left hand side and all exogenous instrument variable on the right hand side. So means that we need to develop one auxiliary regression. Auxiliary regression, we call that as regression, something like this. Okay, this is number one. The first step is we must put x1 as the independent variable. Independent variable, something like this. Okay, independent variable. Okay, put this one. Okay, xi1 independent variable, and we the x1 must be regressed to the z. Okay, to the z. In other way, put the not this one. Actually, when we using the standardized, when we using the reduced form, we using the pi. We using the pi. This is standardized lah. We put using the symbol of the pi, something like this. Okay, the pi 0, and then we put the one z variable. Let's say only z lah, z variable, and also all the exogenous variable from the original model. This one lah. This one you must also include in this model lah, in this reduced form equation. Reduced form equation. Okay, let's see this one, x2i plus this one theta 3 x 3i plus the error. Okay, this is the reduced form. This is the stage 1. You need to regress the S1 to the Z, right? Regress S1 to the Z, the what you call it, the instrument variable, and also all the exogenous variable which is appear in our original model. In this case, because we have the X2 and X3 exogenous, so you must also include into this reduced form model. Reduced form model. Okay, this is the first step. This is the first step. Okay, and then of course the this equation we call it as the reduced form model. Reduced form model. Okay, so and then we need to estimate this model. This you need to estimate this regression. Estimate by dual S. In this is we estimate by dual S, and then we need to get the fit value. So after we regress, we need to regress and they can then get the fit value. Get the fit value of this regression lah. So it will become this one fit value. Or the fit value lah. We can get something like this actually for the symbol. Okay, we can get something like this. Okay, fit value. You need to get the fit value. We get the fit value. Okay, after we get the fit value, and now we do regress the last regression, and the last one regression, and then this regression will become something like this. Just plug in. A very simple one is just plug in something like this. Okay, based on this model, we regress the y, and based on this original model y, put the regress to put the intercept, and we put the not the x, actually we put the x estimated. We want to get the fit value for the x, for the x, and of course put and then regress to the another exogenous variable from the original model. Okay, and then okay, this is referred to this is we call it as the two-stage least square. Two states. This state 1 we need to perform the reduced form model. We need to develop the reduced form model. After we have developed reduced form model, now you need to regress and get the fit value, x hat. Get the fit value x hat. After you get this x hat, and then you can plug in the x hat to, or we replace x hat to the x. Replace the x hat to the x, something like this. Actually it's the same this model. This one's the same. This one same, only for the x1. Now for the x, we replace to the x hat, which is x hat is came from this reduced form model. Came from the reduced form model. Okay. Okay, so the least square estimation from this equation we call it as the instrument variable estimator, and because they can be obtained by the least square regression, they also popularly known as the two-state least square estimator. So some using the IV estimator and some using the two-state least square estimator actually is the identical. Identical. We can call it as the instrument variable, or also we can call it as the two-state least square, because we call two-state least square because we need to doing the two states. The stage 1 is we perform the reduced form model estimation. This one is reduced form, and the second one is the last regression is we using the x hat as head from this reduced form model, we plug in into the original model, something like this, original model, and something like this, and like this, and then we regress. And then of course the value of the beta or beta 1 or all the coefficient we get from this instrument variable estimation is null, is not biased. It's not biased. Okay. Okay, so you